Hello everyone, my name is Wu Yun Mikao, and for this class final representation, I would discuss Lyme disease risk mapping using Earth observation data and machine learning. The article I selected were published by Ganberry and colleges in 2025. The study combined GI, GIS, remote sensing, and machine learning to predict where the blackleg tick population are likely to become established in eastern Canada. Lyme disease is the most common vector-borne disease in North America. It is caused by a bacterium and transmitted through the bites of infected blackleg ticks. According to the CDC, around 476,000 Americans are diagnosed and treated for Lyme disease each year. The disease was first recognized in Lyme, Connecticut during the 1970s. Since then, it has spread throughout the northeastern and midwestern United States and continued to expand into Canada. This expansion is important because climate change is creating more suitable environments for tick survival and reproduction. Because its growing geographic range and increase the number of cases, Lyme disease remain an important public health concern. Early symptoms of Lyme disease including fever, fatigue, headache, and the characteristic bull-eye rash. If the infection is not treated, it can lead to neurological problems, heart complications, and joint inflammation. Severe cases may develop chronic arthritis or other long-term health effects. We should be concerned about Lyme disease because cases are increased substantially over time. As tick habitats expand, more people are exposed to infected ticks. This creates both public health challenges and economic costs related to diagnosis, treatment, and prevention. This map shows the reported Lyme disease cases in the United States during 2023. The highest incidence occurs in the northeastern United States and the upper Midwest. Lyme disease also becoming more common in southeastern Canada. One important observation is that the distribution of Lyme disease closely matches with the distribution of the blackleg ticks. The areas that provide suitable habitat for ticks tend to experience higher disease risk. Because Lyme disease depends heavily on where ticks can survive, researchers have increasingly used GIS and remote sensing to predict where ticks populations may become established in the future. For this project, I reviewed three GIS-based Lyme disease studies. The first study by Ganberry and colleges in 2025 used the Earth observation data, GIS, and machine learning to predict tick establishment in eastern Canada. The second study by Jackson and colleges in 2006 examined how forest fragmentation and landscape characteristics influence Lyme disease risk using GIS and satellite imagery. The third study by Nielsen and Tigenberg in 2023 used GIS to analyze the geographic distribution of Lyme disease cases in Sweden. Together, these studies show how GIS can be used to study disease pattern, environmental risk factor, and public health planning. I select the Ganberry study because it was the most recent paper I reviewed and it used several advanced GIS techniques. The study combined GIS, satellite remote sensing, and machine learning to create high-resolution risk maps. It also identified environmental conditions associated with Lyme disease risk and demonstrates how GIS can support disease surveillance, surveillance and prevention. The object of this study was to estimate the probability of blackleg tick population establishment in eastern Canada using Earth observation data and machine learning from the perspective of the triangle of human ecology. This study focused primarily on the habitat and environment vertical vertices. Habitat variables include land cover, forest type, soil properties, and elevation. The environmental variables included uh, temperature, cumulated heat, and snow conditions. The population component relates to human Lyme disease risk because established tick population increase the opportunities for human exposure. This was an ecological spatial e- epidemiology study that combined surveillance data with environmental information collected from Earth observation sources. Researchers analyzed 933 surveillance sites in Quebec and 155 sites in Toronto, Ontario. They tested several machine learning algorithms using random forest, support vector machine, logistic regression, and GXBoost.